Thank you. Good morning, everyone. So I'm going to tell you about a project I've been working on recently. Actually, since until today, as a data scientist from this company, Countmetry, which is doing consulting in data science for many clients, including SNCF, which is the French train company. And tomorrow, I will be working as a data scientist for my clients, so I will switch to SNCF. I'm going to talk about predictive maintenance on trains. So some part of it I will talk about when I say we is as a data scientist from the team who started the project with a proof of concept, but sometimes I'll say we as SNCF. Although at the end of the session, I won't take questions on the ongoing strikes for those going to Paris for the Euro. I don't have predictions on that, so you can take your questions to the French Bundestag, but I can't answer on that. Anyway, so let me give you some facts first and some data to give you some context. We're 9 billion people on Earth. 2 out of 3 live in urban areas, and when you take Paris area, you have 12 million people. So for the trains, what does it mean? Daily, for a train company, SNCF has to run 14 lines, 2.2 million trips every day, and there are more than 6,000 trains running and moving around all these people. So that puts lot of constraints on the train engineers, and those constraints are very important. So mainly there are 5. Your trains have to be reliable, absolutely reliable. You need to have them available because 6,000 trains to run every day. I mean, you need to be well organized. Safety is extremely important. You cannot make any mistake because lives are at stake. Economy is at stake. It's a huge constraint. The costs for maintenance is also very high. It's important, and a slight change means difference in cost. And also, you have to comply with regulations. So that gives you an idea about how the different parameters engineers have to deal with. So all their trains. They were not very connected, so you had to rely on pure engineering. So there is a lot of knowledge about this, and it worked. But now that so many people take trains every day, this may not be sufficient to run so many trains every day. So you may use connected trains, but luckily today with Internet of Things, you have the possibility to get data from the trains. And now trains are digital natives, such as this one, that replaced the other one that I showed you. So those are Bombardier trains. They are pure, I mean, it's filled with electronics in it. So this is very new. It communicates a lot. They're talking all the time. There is one computer in each vehicle. So for each train, you have 7 or 8 vehicles, and these computers generate a lot of data. So it's not that huge for, I mean, big data people like you, but for train engineers, it's really new. I mean, this type of data arriving in real time, this is completely new in their process. So they are changing their process to eat this kind of data and use it as much as they can to improve maintenance. And you have 40,000 different variables, so a human cannot deal with it. You need nicely designed systems to deal with that. So what kind of data comes from the trains? I mean, they just monitor everything. They monitor material functions of the train. They monitor operations. I mean, you have data coming from the screen monitoring. I mean, just check if there is enough liquid to clean it. So it's really huge. And safety also is important because you cannot run a train if a door is open. It's impossible. So you get all this data and you use it to improve your maintenance. So that's what is in production today. So before classic maintenance, you had a failure, you send a train to a workshop, you do your diagnostic there, and you fix it, and you send back your train. So this is a very low level in terms of value analytics, and I mean, you don't use the data because you just are in front of the fact and you fix it. Then you move to connected maintenance. You can do your diagnostic when the train is in operation, so that you know where to send it, which workshop should you send your train to, and which failure is it about. So you can plan your maintenance in advance. That allows you to have more reliable trains and make it more available as well. And then you move again to a proactive. That means that you do your diagnostic during operations, and you can also, since you have information about your failure, you can prioritize maintenance, meaning you can target in priority failures that can have an impact on operations and leave failures that are less important for later. So your planning is optimized now. The key benefits are, of course, increased reliability, availability, and you reduce your cost, you make the right choice at the right moments, and you move from systematic maintenance, such as what you do with your car. Your car, you send it every 2 years, but sometimes it's not necessary. Sometimes you should have sent it before. Sometimes you can wait two more years. So this is systematic, and now they are moved to condition-based maintenance. So they monitor a condition and they adapt the maintenance according to it. So what's in production today is data analysis. So they have filters and they monitor codes coming from trains. And they say, okay, there is an alert, there is something to do with this train is okay. And so they have the fleet supervisor has a dashboard saying, okay, this train is coughing a bit, there is something to do with it, you should plan maintenance in workshop and remove it from circulation and replace it with another train that's feeling better. The question is now, can we predict failure before they happen? Because here, it's failure. I mean, they are monitoring in real time, so they know exactly when it happens. It's better than before. But if you can predict it like 30 minutes before, it's very important, because then you know, okay, 30 minutes, I have a high probability to have a problem with this train. I'm not going to send it on the tracks. I'm going to replace it with another one. So you avoid impact on hundreds of people. In cities like Paris, it's really important. So even 30 minutes, even maybe 15 minutes is something that you win on your operation. So you'd like to use, I mean, everyone talks about big data. Everyone talks about machine learning, deep learning. So SNCF thought, yeah, okay, we're going to try this. I mean, we don't have big data technologies in our system, in our operation, in our production now, but let's try it. So that may have an impact on operation, but also it has an impact on the knowledge as well. Machine learning could help to reinforce engineering knowledge in the sense that you have experts, train experts, have a very long history of dealing with trains, so they know what's happening, and they have good knowledge of the phenomenon that appear. But sometimes they have preconceived ideas, they have intuition, but something may be non-intuitive. You may have correlations that you can't anticipate according to your expert knowledge, and that's where machine learning could help. On 40,000 variables, a human cannot extract knowledge, but maybe machine learning can add something more. It won't replace experts, but it could add some useful knowledge to it, and produce rules, aging rules about the physics, but also something that may not be explained, but that's known. Another thing also is that when you have new material, you need to learn about how it's aging. And those new trains, there are so many electronic functions in it. It's new, so they don't have 50 years of running this electronic part to build knowledge on. So you need to construct this new knowledge on this new part of the materials, and it's unknown. So machine learning and big data could speed up how experts learn about the aging rules, so that the process that they are putting in place to deal with these aging trains are put in place faster. So that's how this project was born. SNCF thought to start this machine learning big data analysis project. But the thing is that you have operations. You cannot make mistake in production. It's not like marketing. When you make a mistake, you target the clients and you target it wrongly. That's okay. Nobody is going to die. But trains, you don't have room for mistake. So for big data, in something completely new for the industry, you need to prove that it's going to work. And you need to prove if it's reliable or not. And if it's not reliable, there is some uncertainty, you have to control it. You cannot let an artificial intelligence do something that you can't control. So that's why this project was very constrained in terms of time, because we had to prove it worked, and we have to prove it very fast. So the proof of concept part, we had 10 weeks. 2 weeks to learn about the data, get it, and meet the expert, and then 8 weeks to do the problem. So data cleaning, getting the data, crossing things, encountering problems, and then build a machine learning system and predict failures. So that was very, very short. That constraint is important to have in mind, because I mean, when I first learned about the project, I thought, okay, yeah, we're going to do deep learning, neural networks and everything, but you can't do that in 8 weeks. You have to be pragmatic, and you have to stick to existing processes, because it has to go very quickly. If it works, if it seems to work, it has to go very quickly in production, because there are costs associated with it, and if you can gain return on it, you have to put it in production very fast. So there was a push to go very quickly. Although I would have liked, as a data scientist, I understand why they were, I mean, SNCF was so pushy to put in production. But from the data scientist point of view, I would have liked more time to consolidate. But this is a constraint, and it makes sense. So this proof of concept was done, and then since apparently it worked, we put it we put up a pilot. So moving from POC part to production-like, to measure, to be able to measure what happens in real conditions, because there is always a big difference when you work on historical data and real data, hot data coming from the trains. And right now, we are at the beginning of this phase that should last for 6 months. We are just going to watch what's happening. If the failures are predicted correctly, which are predicted wrong, to know what's happening, because we don't know what's going on in real condition yet. And then, if it works, if we manage to tune everything, we're going to put it in real production. And with this comes the real problem, the change management. Because you're pouring a machine learning into an existing process that you cannot change. Existing processes have been there for a long time, and they are there for good reasons, so you have to stick to this and adapt, but evolve mentality, evolve how experts deal with that, and that's our questions today. So that's the context of this project, and I'm going to tell you the road that we have done since about the beginning of this proof of concept. So the first challenge is that failures, I know people are going to say that's not true, but I tell you it's true, they are very rare. Very, very rare. I tried to ask them to produce more failures, but somehow they didn't want to do it. So we had to deal with this. And for machine learning, you don't have examples about failures, but you still have to learn from it, so it's very difficult. A second problem also is, although trains have been running for a long time, but these trains have been running for 2 years at most. Today it's been 2 years. So at that time we had like 18 months available. That's very, very small. And that's a problem to have efficient machine learning. Another challenge that most of you may not encounter, if you take a young company such as Zalando, I know people are here from Zalando, it's from 2008. Okay, fine, so a few years. You take another company, Google, 1998. That's fine, older. But this company are digital natives. When you take SNCF, it's from 1938. That means that if you're trying to do big data, if you're trying to do data analysis, you have to deal with data and processes and information systems that are very old and that were born long before big data. So that comes with challenges that big data engineers don't encounter every day because they have nice logs produced by new applications and it's all very nice. But, for SNCF, it's slightly different. So the challenges about data, first is data quality. You have unclean data, like everywhere. But in addition, you have data, it's not clean or not reliable for different reasons. For trains, for instance, we wanted to do supervised learning, so we had to build a target. So the target was a failure. But how a failure is identified, it comes from many different sources. So either the train realize itself that there is a failure. In that case, the time of occurrence of your failure is precise because it's new electronic system. But it may be your driver. Your driver has a problem, so he realized that there is something. There is something on the door, for instance. Okay, so he stops the train. He gets down his cabin, walks along the tracks, check on the door, close it manually, and then comes back to the cabin. He calls someone, he pushes a button, but the time of occurrence of your failure is completely imprecise. You have no idea. Maybe it was 15 minutes before it's your information, maybe it was later. There is uncertainty about the time. It could be the fleet supervisor. So there is a lot of uncertainty in your processes. And when you build a target, you're a data scientist, you like when it's precise, but the target is not precise. Another thing is you need to identify which type of failure it is. So you need feedback from technicians in workshops. That means they are entering information at the end of their day after fixing several failures on train. At the end of the day, they go back, they enter this manually in the system. That means sometimes it's inaccurate. They may be in a hurry, there may be an emergency somewhere, so there is also something very imprecise, although it's a modern way to produce data. It's 21st century, but still, you have to deal with that. So you may need to do NLP to do this, but you add more noise in your process. So data is generated through various and very complex processes. Trains, it's like a living organism. So there are many functions, and it's difficult to deal with it. It may not be big data, but it's big in the sense that it's completely heterogeneous. And sometimes getting data is difficult because there may be contracts with a train constructor that doesn't allow the train company to get some type of data for some reason. So it's a long process, and in 8 weeks, some part of the data we would have liked to have, we didn't get. But we had the core data, which was the data coming from the trains, the codes and operation data. So another funny challenge is that we did not anticipate it, is that trains dream when they sleep. So I didn't know about that. I'm sure you didn't know about that either. But yes, I mean, in the system, in train, computers generate codes. I mean, they analyze physical data, vibration, and everything. And then they aggregate this data and they say codes. So there are about, for these trains, there are about 2,500 different codes. And that was our core data. And there was one code saying, OK, the driver entered the train, he pushed a button, and he started the train. And there was another code to say the driver got off the train and finished his mission. And when you want to predict failure, you don't want data coming from trains outside of operations, because there may be a technician passing by and, I don't know, connecting a cable. That sends a code, but it has no meaning about operations. So you have to remove this data. So we thought, OK, that's... we did not anticipate that. We didn't know that trains would talk in their dreams. But they do. So you have to take out the data. And we tried this. And then, actually, the performance of our machine learning system was very bad. And we didn't know about that. We didn't know why. It turned out that, actually, the process of terminating the mission is wrong. So the code that we were targeting to take off the useless data was wrong. So we were learning about the train's dream, but it wasn't very useful. So actually, we had to get the data monitoring, so from a completely different information system, data saying this train started at this hour from this station, and it ended at this hour from this station. So that's OK. Data exists. But that adds a lot of complexity in your system, since, OK, before you thought you could rely on one source of data that's precise. Actually, it's not precise, so you have to cross it with another source. And you have to filter out data. That means that in production, it has a cost in terms of calculation. It's really important. And you may lose 2 weeks in your project trying to fix this problem. And also, since the data is produced in production, you cannot go back to the systems and ask the people to change the thing, because people having a hand on how the computer sends data is the constructor. So you have to go back and change the contract with the constructor. It's impossible to fix, in a short time. So you have really this constraint that your system is really complex and involves many different entities. And that's different from many companies that you know about, I think. Anyway, so how did it work? Very quickly, because I think you know about this. So we have sequences of code. And since we are doing supervised learning, we need to aggregate this to have one line with one target saying, OK, at this hour, there was a failure. This time, there was not a failure and everything. So you had somehow to take some time on which you monitor your data, and you count the number of each code, things like that. You make means, you calculate the average duration of a code, things like that. So you aggregate your data so that you have sequences corresponding to different trains. And after the sequences, like 30 minutes later, you say there was a failure or there was not a failure. So that's how we did it. That's very simple, but we had to be pragmatic and go fast. And we thought supervised learning would work because it's stable, it works almost all the time. You take random forest, it's going to work anyway. It may have lower performance than neural networks. But in 8 weeks, there is no way you can develop a neural network and do deep learning on this. So that was the safe approach. We knew were going to work. So that's how it works. So we have identified faults in all the trains all the time, and to generate lines that leads to a fault. We take the fault, we take horizon prediction, so like 30 minutes, 1 hour, whatever time you want to go in advance, and then you monitor your code for some time. So in this example, on 4 hours, I take 4 hours of code, I aggregate, I look at it, I feed it to a machine learning system, and it's going to learn whether or not 30 minutes later it has led to failure or not. So that's how you do with your Kaggle-like problem. You have a history, you separate it, you learn on 70% of your data, and then you test it on 30%. But that's history. And real-life data, it's different, because you have hot data. This is cold data, and it may change. And that's actually what we are seeing today. I mean, it changes. It's not the same. So you need your data in production, and you need to have it work neatly like that. But when you do a proof of concept in 8 weeks, your data scientists work like that. So, I mean, it's difficult. You have your data engineers that know about Spark and are playing with a cluster, and your data scientists work with Python and scikit-learn. I mean, that's me, I know. And we had to communicate with the data engineer, transposing our code that was designed very quickly, very pragmatic way, but they had to put it in production and make it work. And that was difficult. We didn't think at first in terms of distributed computation. So we had to reorder our code so that it would be possible to distribute computation over trains. But that took some time to design. I mean, it was different. Also, writing efficient Spark code, translating from a POC written in Python, I thought it would be easier because Spark, they tell you we have a data frame. It's very much like Panda's data frame. Well, actually, that's not really true. Here, it's very difficult. So it took a lot of work to transpose it. But in the end, it's okay. So, but there were questions also. How do you validate that your pilots reproduce what your proof of concept did? There are differences in implementation. I didn't know about that, but less is not the same as less than equal in Python and Spark. So when we would try to compare at different points how our data was prepared, so we took data from the proof of concept and we tried to compare the data with the pilot. But there were lines didn't match, and it took us some time to realize that less was not less than equal. I mean, you don't anticipate this kind of problem. So we thought we would develop this in 1.5 months. Actually, it was slightly more. And there is the question also, when you want to compare predictions and prediction performance between a proof of concept and a pilot. So we had the random forest implemented in Python, in scikit-learn, and we had the random forest implemented in MLlib. But actually, random forests are somehow random, so we cannot compare data with data. It's obviously not going to be the same. So you have to design new tests, statistical tests, to be able to say, okay, it's the same, it's not the same. You can't compare train by train. It's impossible. So, I mean, this is new compared. I mean, machine learning, there is some randomness, there is some difference. It's not the same as doing a proof of concept with a fixed application. When you put machine learning there, you have new problems. So what's our stack? So we have Hadoop cluster with Spark. So all data preparation and the machine learning is done in Spark. And there is some reporting part that we do because we need to send back information to the experts. So we have the web application that's asking Elasticsearch where the results are stored. So that's AngularJS that produce reporting for the experts. The cluster is quite small. I mean, this is the beginning, and the team is learning and everything. And there is a question. Data we have is not so big. So we could have actually stick to Python and put it in production. But we anticipate that very soon there are going to be more trains generating more data. So we thought, OK, let's start with this and learn right now, since we have some slack about time, so that tomorrow when we have real big data, we have encountered some problems and we are starting to work with it. So how it works, I'm sure you know this architecture. So you have an incoming flux, you prepare data, you store it for the training of your problems, your models. You have some reporting on how it learned, how well it learned. And then you update your model that are in production and that works on hot data. And this produces a stream of near real-time predictions that's sent to experts so that they can use it. I'm going to skip that because I don't think it's so important. We could come back to this if I have questions, but that's how we deal with data incoming from times. It's not so interesting. What we are aiming at is to have prediction, so it predicts 30 minutes before. So at some point we expect to have, OK, I have one train that's coming out of a workshop, and then at some point it's aging, things are going wrong. So we expect that at least we can rely on looking at the history of prediction. When failure is going to occur, at some point, probably your machine learning is going to say, I'm not sure something is going wrong. And then half an hour later, it's saying, I think it's really going wrong. And then you can see it increase. So that's why how you can take decisions on this. And when it reaches some alert threshold, you can send it to a workshop, you fix it, and then it comes back to 0. So that's the reporting for training. So we monitor the performance on the history. So we check that machine learning system worked correctly. And that's the reporting for the experts. So they have their trains 1 to 182, and the red ones have problems. And they can click on it and have a list of all the predictions for all the functions of the trains. So there is the door function, the motor problem, every function on the train. There are about, it's like meta functions. Different equipments that are monitored, and each has a prediction, and it tells which is wrong about it. So in this case, it's video surveillance. And now I'm going to speed up because I took too much time to explain. We have real-life questions. In real life, so we are here, but we have to implement this in an existing process. And I already mentioned it. You have to convince your expert that your machine learning system, it's a black box. So, and they have to be convinced they can rely on the prediction, which are, by essence, probabilistics. So you need to control it. You need to be able to rely with it. And how do you deal with false positive and false negative? You cannot send all your train in workshop, because at some point your technician is going to say, OK, but you're sending me trains that don't have a failure. And how do you tell them, yeah, OK, this train I'm sending to you, it doesn't have a failure, but it's going to have it. If you don't explain why you're saying this, it's impossible. You don't know what decision to take. The technician is not going to know which door it has to fix. So it's difficult, and you have to read your machine learning models. and extract knowledge from your random forest. And it's difficult scientifically, in the terms of technology, and in terms of change management. That's where we are right now. So the next step is using the pilot in test to find the best parameters. I mean, how long should we wait, and how long should we monitor data to predict correctly? Number of trees, depths, I mean, that's long to choose this in production in real life. And we have to choose area threshold. At when do you take your decision? When do you stop a train and send it to a workshop? This has costs, and these decisions had to be made with reliable knowledge. And although there are many other questions, the data evolves. There are updates of your computer in trains. So data evolves, and your machine learning is not stable with this data. How do you deal with that? How do you ensure the stability of intelligence in production? What is a unit test for a machine learning system? I have no idea. I mean, I have some ideas, but it's new. People don't have answer yet for that. And so that's our next steps. And how do you protect against malicious attacks? And that's a question. It's more like my own questions. SNCF is not worried about that yet, but when you want to really annoy a train company, you can try to pour false data for your machine learning. It's going to learn nonsense. And if it's in production, it's dangerous, because if you manage to feed stupid data to your machine learning and it's in production, it's very dangerous. How do you protect against that? And how do you design alerts to see that your machine learning is moving from what it should do? It's difficult. So I'm going to skip the lessons learned. You will have this presentation available, but you need to, basically, your data scientists have to think about production a lot before than what was done here. But that's okay. Now we are changing the way to deal with it. And I had some nice things about what's going on right now. Right now, actually, we are trying in proof of concept using neural networks, but the thing is that it's very, very unstable. The reason being that the data evolves with time, and it's really, really unstable. That's why supervised learning is a lot safer than neural network and supervised learning. So with that, I thank you for your attention, and if you have one or two questions.
Thank you, Heloise. We have a question here.
Thank you for your talk. Very interesting problem. I'm just curious, what kind of accuracy can you get out of that system with so many variables and so little time to learn?
You mean in terms of predictions?
Yeah.
The accuracy. I mean, it's not very easy to answer this question right now, because I have the answer on historical data. But actually, accuracy is in itself not so interesting. The question is more, how much more accurate are you than what's existing already? So we try to compare how, I showed you filters that are in production today and work on real-time data. And we compared these alerts coming from system in production to the alerts that we could have generated with the data. And we had, we of course has false positive, that's costly, and false negative, it's costly in terms of people and impacts on operations. And we could prove, I mean, we would see, I don't have the numbers in mind, and it depends on the parameters, the number of trees you have in your thing, but there were some gain. I mean, there were, the thing is that you target the highest probability first. So when you take like the 10 first trains, it would I don't know, what's in production would say, would detect 2 failures out of 10, and we would detect 6 out of 10. So there is an increase. And anyway, even a slight increase has real impact instead of cost. So that proved the expert that what the approach was good. And it depends also on which function you're talking about. If it's the doors, for instance, we were a lot better than for air conditioning. Since air conditioning, actually, you have problems most of the time in June, July, August, so we didn't have so many examples. So it was a lot less, it was not as good as for the doors.
Wow. I'll just go there and come to you.
Thanks for the talk. My question is, you were saying that you have about 2,000 variables. Were you using all of them to train on all your functions, or were you do a pre-selection and saying, okay, only those 100 are relevant for the AC and the other 200 are variable or are important for the doors? Yeah, and who gave you that information?
So it's a very good question. Actually, the experts, what they do is exactly that. They have 2,500 codes, and well, since the beginning of these trains, they monitor almost manually. And now they also the constructor, I mean, they know how the codes were generated, but it's a very long process. But they know code 8,200 corresponds to this small part of this function of this door. But they ask us to, okay, we know how to do this. It's long, but we are doing it. What we need you to do is to take all the data. You don't filter it, because we know we have intuitions, and we know there are correlations, there are non-intuitive interactions between functions on the train that occur, and we don't know about it. It's weak signal, and we want you to use machine learning to extract this weak signal. So actually, we took everything. And we crossed also with material data, other data coming from different. We basically tried to take everything we could without filtering.
Thanks.
I'm afraid I won't be able to take more questions because we are running out, but you can check with Heloise and she can take it offline. Thanks for your understanding.
Thank you very much.